All right, today we're going to talk about rational functions and asymptotes. Asymptotes are kind of a side effect of rational functions. Rational just means fraction. So if you look at a function like the one I've got here, f of x, it is a fraction. And the big thing you cannot divide by is 0. So if there's an x in your denominator, there's going to be some value for x that if you plug it in, you end up dividing by 0. And that's kind of the name of the game, is find the x value that will cause you to divide by 0. And then there's asymptotes and there's also wholes. So we'll have to classify what kind of problem we have going on. But that's kind of the name of the game. Finding the problems, finding where you would end up dividing by 0. So the first step with these is to take your denominator and set it equal to 0. And once you've set it equal to 0, so in this case, x minus 2 and x minus 1 would be your two factors for that trinomial. Each one of these would get set equal to 0 separately, so x would equal 2 and x would equal 1. Now these aren't solutions, these are problems. Again, wherever this denominator equals 0 is a problem. So I want to set this equal to 0, and I'm solving to find which x values will create a problem. So these aren't solutions to the function itself. Not solutions would be x-intercepts. These solutions tell me, all right, these two x values will, if I plug them in, I'll be divided by 0, so these are problems. And then I put them up here, x equals 1, x equals 2. So I really want to explore what's going to happen as we try to plug these in. So I'm going to switch over to Desmos for a second. Let's take a look at the graph and just kind of see what's going on. There's going to be a problem at each one of these points. But let's talk about what type of problem we have and how to figure that out. So at x equals 2, we've got a definite break in the graph. That's an asymptote. At x equals 1, I don't really see a problem. And you'll have to actually scoot along the graph here. If I can get right on it, right at 1, it'll say undefined because there's a hole in the graph. Okay, we'll get into that more about how to find those algebraically in a few minutes. But I want to take a minute to run through with Desmos and kind of look at how we can figure out what's going on at these points. And before I do that, just kind of show you the chart that the approach I want to take. We know if we plug in, say, 2, we're going to get an asymptote. It's not going to exist. The function's not going to exist there. So this is kind of the calculus approach. You'll take this approach a lot in calculus to try to see what's going on. If we know we can't quite get to 2, then let's get really close. Let's see what happens when we plug in 1.9, 1.99, and a whole bunch of 9s. See what the pattern is and see what we're getting really close to. And that's getting that idea of a limit. If we can't quite get to something, let's get really, really, really close. Let's see what we're approaching. So we'll keep on top of that limit idea as the year goes on. So I'll switch over to Desmos, and then we'll take a look at what's going on with that.
So in class, I would have filled in that chart with you. We'd have made it really interactive, but I'm just going to do it on Desmos in here. So what I've done is I've taken our example and made it f of x. And below here, I've done f of, and I'm going to get really close to 2. So I'm going to start with 1.9 and then kind of go from there. 2 is an asymptote. So let's see what happens as I get really close to that. So down here, it says it's equal to negative 10. So let's put in another 9. Now it's equal to negative 100. Another 9 is 1,000. And it's the more 9s I put in here, you can see it's getting really close. Eventually I called it undefined, but it's getting really, really far down. The y value is getting really big, but negative. So negative 5.6 times 10 to the 14th, that's way down the graph. So it's getting really close to negative infinity. And of course, if I put in 2, it's going to say undefined. What if I did 2.01? That would be 100. 2.001 is 1,000. So the more zeros you put in there, the closer it gets to positive infinity. So that kind of shows us the graph's going up on one side, down on the other. Now, the other thing that happened was at 1, we had a hole in the graph. So it should show up undefined if I can get right on it. If I can get it to stay there, it keeps dancing back and forth. So it will show an open circle, but you got to click right on it. It won't stay there. It does say undefined right here. So let's try 1.01. All right, well, it's showing it being really close to negative 1. And the more zeros we put in here, the closer and closer it gets to negative 1. Sort of dancing around it there, but it's getting really close to negative 1. And let's just try maybe 0.99 and go that direction. And you can see it's getting really close to negative 1 that way as well. So This will become what we call removable discontinuity, and I'll explain that more in the next example. But we can conclude exactly where that point is. And actually, when you label the hole, you got to be careful to show the x-coordinate and the y. So you do have to find the y-coordinate. Now, this was sort of a lazy approach or a cheating approach. We're using a graph to do the work for us. So we'll do the algebra in the next example.
All right, in this example, you're supposed to find all vertical asymptotes and holes. Now I'm going to do this entirely algebraically, where we took a graphing approach in the last one. So the first thing I would always recommend is factor whatever you can, especially the denominator, but if you can factor the numerator and the denominator, go ahead and do both of those. Now, if the factorings give you trouble, we can talk about it more. I'm just going to kind of blow through that part. The factors that would make this work would be x plus 2 and x minus 1. The factors that would make this work will be x minus 3 and x plus 2. Now, it's very tempting to say, oh, common factor, you cross it out. Now, eventually you'll get to do that, but just hold on for a second. Don't get ahead of yourself. Because the first thing we got to figure out is, where are our problems? So, if I divide by 0, we've got a problem. So we need to set this denominator, and it's easier to just do it in the factored form. Set it equal to 0. And you just set each factor equal to 0. That's the easiest thing to do. So if x equals 3 and x equals negative 2, we got a problem. Okay? So I'll put the graph up in just a moment, but again, let's focus on the algebra for now. So hopefully it's not too crazy to see that. If I plug in 3 right here, 3 minus 3 is 0, plug in negative 2 plus 2 is 0, those are going to create problems. So we got to classify these problems as what they are, vertical asymptotes, or holes in the graph. All right, so now's the part where you can cancel out or divide out common factors. X plus 2 was in common, and that's a hole in the graph, or something, what we'll call in calculus is a removable discontinuity. All right, big word, I know. A lot of y'all were asking about continuity back in the first chapter. Simplest way to put it, continuous function, I can draw the whole thing without lifting my pencil. As soon as I have to lift my pencil and do separate sections or there's a gap, that's discontinuous. So a hole is a discontinuity because I'd have to lift my pencil and scoot over top of that gap and go on. But it can be removed. And then that's something you'll spend some time talking about is, can you remove the discontinuity, or is it just a terrible break in the graph you can't fix? A hole is a removable discontinuity because I can figure out exactly where that hole is and I can fill it in if I need to. So the hole is going to happen when x is negative 2. Now, we're not quite done because we need to actually figure out where the hole is. There's a y-coordinate that's going to go with that. But for now, when x equals negative 2, that's a hole in the graph because that's the term that divided out. The other one that was not able to be removed, that one's going to be your vertical asymptote. So x equals 3 is your vertical asymptote. So now before I explain the y-coordinate for the hole, I'm going to go back to your Desmos graph. So here's our function graph. X equals 3. Here's our vertical asymptote. Again, that's a non-removable discontinuity because you cannot fix that. That's going two separate directions. That's going to negative infinity. That's going to positive infinity. You cannot tie those two together. You're not fixing it. But over here, at negative 2, it's undefined, but it looks like it's really close to something, and I could probably figure out exactly where that is. Looks like it might be about 0.6, but we need to make sure. So I can kind of take that approach where I get really close to it, and I can figure out exactly where that hole should be and give the point. The way you fix this is a piecewise function. This function is one piece, and when x is whatever, or x is negative 2, then y is one particular value. That's how you would fix this as a piecewise. So here's what I really want you to see with this example. We can't really remove this discontinuity, this asymptote. We can remove this. Now, the next graph I've got that should look exactly the same is the reduced form, x minus 1 over x minus 3. Now watch what happens when I go to negative 2 here. I should actually get a result. If I can get it to land right on. All right. There it is. It is 0.6. Okay? So the thing I want you to take away from this These two functions look exactly the same because they are exactly the same. The only difference is that factor that created this hole, that x minus 2, has been divided out. But other than that, they're exactly the same. This is a scaled up version of the other function. So the blue one is the simple version. The black one is the scaled up version. It's been scaled up by x minus 2 on top and bottom. And that's kind of weird, but that's what's going on. That's what created that hole in the graph. So we could remove that discontinuity. So algebraically, the way you're going to find that, we know that at negative 2 we have a hole. So if this is the new function here, a reduced version of it, x minus 1 over x minus 3, then really all I need to do is plug in negative 2 in this reduced version that no longer has the hole in it because it's been divided out. And that's going to tell me my y value for where the hole is. So let's rewrite this. Our new function, it's really the same function, it's been reduced down a little bit. So I'm going to evaluate f of negative 2, but with this being the new simplified version we're going with. So negative 2 minus 1 over negative 2 minus 3 is negative 3 over negative 5, so that would end up being positive 3/5. So negative 2 and 3/5. Oops, there we go. That's the hole in the graph. So for the final answer, make sure that you are including the x and the y coordinates. Next example says to find all vertical asymptotes in holes. So same directions, new function. All right? This is going to be kind of interesting. So there's nothing to factor on the top. There's really nothing to factor on the bottom. So I'm going to go ahead and skip to the part where I take my denominator and set it equal to 0 and try to figure out where any problems will happen. I mean, there's an x in the denominator, so there's got to be some value of x. If I plug it in, I'm divided by 0. So let's find that and see where it is. So 3x squared equals negative 1. X squared is going to equal negative 1/3. And I'm going to need to take a square root to solve that. And I'm going to stop right there because x is going to be complex. I guess I could go further. It's I plus or minus I squared of 1/3. We could rationalize that a little bit more. But that's where we're ending up. This is two complex solutions. So long story short, think about where you're going to graph this thing. You're going to graph it on your xy coordinate plane, your real plane. There's no place for complex numbers on the real plane. So the only place that could ever have given you a problem exists in the fourth dimension in complex numbers. I know, it's crazy, but simple version of that is there's nowhere in the real plane where that comes up. So there's no real number for x that's going to give you a problem. So there are no asymptotes or holes in this graph. If you want to just put an answer, there's none. And to show you graphically what's going to happen, it's kind of an interesting little graph here. It's got a little whoopsie-daisy in the middle or something, but it's not, there's no asymptotes, there's no holes, it's just sort of like, kind of like a little wave, I guess. All right, so now we're up to horizontal asymptotes, and what's kind of interesting about these is you can cross a horizontal asymptote. A vertical asymptote, the graph's going off toward infinity, and you cannot cross that or ever get to it. But a horizontal asymptote, you can cross. On the last example we just did, that's a good one that shows that you can cross a horizontal asymptote because you do have long-term behaviors getting really close to 0, or end behaviors getting really close to 0 on both ends. But it's definitely going across that in the middle. So again, it's all about what does it do way off toward infinity for x and negative infinity for x. Way off on the far ends, what's it doing? That's the horizontal asymptote. It's long-term, what's it getting close to? So it's not a barrier you can't cross. It can be crossed. Now in the end, there's 3 basic rules you can just memorize, which is okay, it will get you through. Remember, the whole theme of the class is understanding what's going on. Not knowing how to do it, but knowing why it works. All right, we're going to take a couple approaches here, but again, it's all about end behavior. As you go way off to the right, as x gets bigger and bigger and bigger, or if you go the other way, if x gets smaller and smaller and smaller, more negative, what is your graph getting close to? What is your y value getting close to? So let's put something that's pretty big in here, like say 1,000,000. So I'm going to do f of 1,000,000. Yeah, I'm going to probably kind of cheat my way through this a little bit, but that would be 1,000,000 plus 5 on top. On the bottom, we'd have 1,000,000 squared minus 3,000,000, and then plus 5 at the end. I certainly could have combined a couple of those things, but just kind of think about what that would be. If you had 1,000,000 squared, that would be one with 12 zeros. So, let's see, million, billion, 1 trillion. That would be a trillion. So just kind of think of it in terms of maybe money. Not that we can visualize most of this amounts of money, but just in case. So, if I had $1,005,000, okay, that's a lot. How does that compare with having a trillion? Well, a million's nothing compared to a trillion. So, what's going on here is no matter what you have on the top, the denominator is going to be so much bigger than that anyway that this is going to get really close to 0. And it's never going to quite make it to 0, but the bigger number you put in for x, the denominator is always going to be so much bigger than that that this is going to get really close to 0. So let's take a more calculus approach to this problem now. Plugging in a really big number for x is a good way to think about it. But we want to think about what happens as x approaches infinity. So this notation, something you'll see in calculus quite a bit, what we're saying here is, what is f of x, or y, as x approaches infinity? So as x goes this way, as far as you can go, what are your y values getting close to? What are they doing? What's their behavior? So instead of doing equals from here on out, I'm going to start doing a little arrow saying that this function for y, my y value is approaching something. It's not going to equal that, but it's going to get close to it. So I'm going to stick some infinities in here. It's going to look really weird, but let's just kind of think about how it will play out. So infinity plus 5 over infinity squared minus 3 infinity plus 5. And it's kind of that same deal of whatever is bigger is going to dominate everything. So this is kind of not algebraic, but just kind of run through it with me, and I think it would make sense. In terms of infinity, adding 5 doesn't do much. So I'm just going to forget about those things out there that are just constants, because they don't add hardly anything in terms of infinity. Now, this is infinity, this is 3 times that. And this is a question that always comes up. Now, there are different sizes of infinity, but it's more like a rate. 1 infinity is getting to infinity slower than 3 times infinity. So it's kind of like how fast you're getting there, more than size, because infinity is infinite. Don't get too caught up on that. The biggest thing going on here is, in the end, if you have infinity squared and you subtract an infinity or 3 infinities from it, again, think of huge numbers. A huge number squared is so much bigger than like a million. You got a trillion versus taking away 3 million of it. If you had $1 trillion, you're not going to notice losing 3 million probably. So this stuff's really not that important either. Really, the leading coefficients are all that matter. Or not coefficients necessarily, just the leading terms. So what we end up with in terms of what's kind of driving this result, you got infinity divided by infinity squared. All right, so think about how that would play out. If these were just normal variables, that would end up being 1 over infinity. Now, something we've talked about a few times here and there. Infinity and 0 are opposite ends of the spectrum. They're ideas. You can't get to them. But 1 divided by infinity is 0, because it's the opposite of 1 divided by 0, which is infinity. So this is actually approaching 0. So the case, really, anytime you see a bigger power of x on the bottom than on the top, your y value long term is going to approach 0. So you're going to have a horizontal asymptote at 0. Now in this example, we'll kind of try to not do all that other infinity stuff every single time. There's some shortcuts we can start to look for. Now here, the first terms are both x squared. And as you think about plugging in really big numbers for x, these x squareds are going to dominate everything. The other stuff's just not going to matter so much. Again, think about plugging a million in here. A million squared is trillion, and if you take away 10 million from that, it's not going to be very noticeable. If you add $5 to a trillion, that's barely noticeable whatsoever. So really, and this is kind of, again, not algebraic, but these things aren't going to play much of a role. This is really going to drive what's going on. As you put really big numbers in here, this is what's going to matter. So as x is approaching infinity, if we start thinking in terms of plugging infinity in, then 6 times infinity squared over 6, or 2 square, infinity squared, and reduce that down, well, the infinity squareds, if they were any other variable, would just divide out. 6 divided by 2 is 3. So long term, let me kind of write it in this notation for you. As x approaches infinity, your f of x, or y value, is approaching 3. So that's your horizontal asymptote at y equals 3. The last case is going to deal with when you have a power or an exponent on top that's bigger than the exponent on the bottom. So if we take the same kind of approach here, as x approaches infinity, and again, only the first term's really going to matter. Adding 12 to infinity or subtracting infinity from infinity squared, it's not going to matter much. Adding 1's not going to matter much. So if you treat it like any other variable, 2 times infinity squared over 2 times infinity, well, one of those would divide out, and your 2's would divide out. So in the end, it would approach infinity. So if your y value is approaching infinity as your x goes to infinity, I mean, that's just going to keep on going. It's just like most of your polynomial functions. As you go out further, you go up further. That's really what that part's saying. So in this situation, we don't have a horizontal asymptote, but we will end up with something called a slant asymptote. And I believe your book calls it an oblique asymptote, but slant's what we're usually going to call them.